I will present the project towards the overcome of performance pitfalls in data stream mining tools for the IJCNN 2021. I am Lucca Portes, and together with me in this project are Professors Marco Antonio and Jean Paul. Me and Jean are from the Pontifical Catholic University of Paraná in Brazil, as Marco Antonio is from the Federal University of Paraná, also in Brazil. Let's first talk about data stream mining. It is an emerging topic, a hot topic nowadays due to the ever-growing amount of data that we have due to corporations and enterprises storing more and more data. But many challenges must be taken into account when dealing with this environment. One is that we have a potentially infinite amount of data. Data always keeps coming. We also have to expect a high throughput. And due to these points, we have time processing limits because we can't lose too much time with single instances. And ideally, data stream mining algorithms should stand on three pillars: high accuracy, a reduced processing time, and an efficient memory consumption. But unfortunately, this is not always the case. We have nowadays two main libraries for data stream mining. One of them is Moab, which is made in Java. It is not so recent library. It is already widely used by the scientific community in papers. And we also have Scikit Multiflow, which is made in Python. It is a newer library, and it's still in process of being adopted by the community, so it's not widely used in scientific papers yet. About Moab, it has some limitations, most due to the language it is written on, which is Java. Java has a slow learning curve when compared to Python and requires much more expertise to guarantee that we have a memory leak-free software. And Java cannot easily bind to lower level language, which limits its maximum speed it can achieve. Well, here are some benefits of Scikit Multiflow, mostly due to the language it is written on again. Python has a faster learning curve than Java. It's also easy to guarantee that we have a memory leak-free software, which is desired when dealing with data stream mining. And Python is also implemented on C++, so it can bind to any shared object compiled by a lower level language. This can dramatically increase the speed of libraries written for Python. But one limitation of Scikit Multiflow, the library Scikit Multiflow, is that it does not take advantage of low-level language, so it has a severe speed deficiency. Here's an example. I have a code from Scikit Multiflow here versus an optimized version of the same code, but using only a Numpy function. Numpy is a library for dealing with arrays in Python, but is written in C++ and Fortran, so it's highly optimized. And here's the code. This is from Scikit Multiflow. First, a list is instantiated for starting the predictions. Then we iterate in a matrix of probability, and we get each row of the matrix and pass it to the numpy.argmax function, which will get our class value or actual class value from the probabilities. Then we append this class value to the list that was created before the loop. And here is the optimal NumPy code that can be called to do the same thing. You simply pass the whole matrix of probabilities to the NumPy argmax and pass the number, the parameter x is equal to 1. This will make NumPy do all the computations much faster in the whole matrix and store it in the same variable. Here is a difference of time calling the pure Python. It starts from Scikit Multiflow, which is a little more than 2 seconds it took to run. And while the NumPy code here took 0.1 second. So our proposal here is to demonstrate that a data stream mining library in Python can both have an efficient use of memory and have a reduced processing time. Our protocol is the following. We propose the rewriting of some Scikit Multiflow classes, which are naive base, C generator, and random RBF generator. And the Prequential validation scheme, so we can validate our experiments. We also wrote them in different programming languages, which are Rust and C++, and inside C++, we use the standard library and the Intel Intrinsics library, the AVX. We chose Rust here because we wanted to see how it would perform against a classic low-level language, since it is a newer low-level language. And so in total, we have 3 different implementations for each one of the classes. We first have a result for the Prequential with the C generator for an increasing number of instances, so you can see the impact of those. In the y-axis here, we have the processing time in seconds, and the x-axis we have the number of instances. We can clearly see that Scikit multiflow was by far the worst one, followed by Moab, which is worse when we have a low number of instances. And all the other implementations here were pretty close together, followed with C++, with the standard library, AVX, and the Rust implementation. You can see in this detail table here the actual processing time for some of the instances for 20, 50,000, and 100,000. For 20 instances, you can see that the difference between Scikit multiflow and Moab, Scikit multiflow is actually better than Moab, while all the other implementations were pretty much the same. For 50,000, Scikit multiflow is already way worse than Moab, while the other implementations are pretty close together, but Rust is the fastest one, followed by C++ with AVX. The same pattern repeats for the 100,000. Scikit multiflow is the worst, followed by Moab, and Rust is the best one, followed by C++ with AVX, and then C++ with the standard library. Here are the results of the Prequential with the random RDF generator with 50,000 instances with an increasing number of features, so we can see the impact of features instead of instances. We have a processing time on the y-axis and number of features on the x-axis. Well, again, Scikit multiflow is the worst one, this time from the beginning, followed by Moab, which is worse when you have a low number of features, and almost tied with C++ with the standard library when you have a higher number of features. And then followed by C++ AVX, and then the Rust implementation. Here in the detail table, we can see that for a number of features, 252 and 102, Scikit multiflow has a huge gap for all the other implementations in all of them. While I was interested to see the gap between Moab and C++ for 2 instances is much bigger than the gap for Moab and C++ for 102 instances. While the difference between C++ with the Intel Intrinsics, the AVX, and Rust is also bigger with a low number of features, and also smaller when we have a higher number of features. Again, Rust was the best performing one. Here are the results for comparing memory. We have Prequential with the C generator with 100,000 instances. In the y-axis here, we have the memory usage, while in the x-axis we have time, which was normalized for the sake of clarity. We can see that Scikit multiflow has the worst results, but it's not necessarily bad, because this pattern here, which is to quickly increases its memory usage and stabilize it for the rest of the execution, is desired when dealing with data stream mining. While Moab has a lower usage of memory, but this pattern here is not so good because it keeps increasing the memory usage as the time passes, and is not desired for a data stream mining algorithm since you have an infinite amount of instances. While all of the other algorithms here are pretty close together and have the same behavior, the same pattern. Here in the detailed results, you can see that Scikit multiflow uses a lot more of memory than Moab, and much more than the implementations of C++, both with AVX and standard library and Rust. And implementation that used less memory was the C++ one. So in conclusion, a library for mining data streams in Python with high performance and an efficient use of memory is feasible. In fact, there are projects with that goal, such as River, which is merging a scikit multi-flow with another library. It's called Cream. The slow implementation of all was C++, of our implementations was C++ with the standard library. This is due to the high level of abstraction that the standard library provides. And Rust outperformed C++ with Intel Intrinsics with AVX because Rust has an efficient auto-vectorization of its code. Here are the references used in this presentation. Thank you.